So before we actually get started with the meeting, first of all, this is how we're going to be able to contact you. Everyone join the Schoology. Like, get out your computers right now and join the Schoology. There will be important announcements on that as far as like when we're having meetings. Probably most of you guys hopefully noticed today we're meeting in a different place than we were 2 weeks ago. So you'll never know unless you check the Schoology where we're going to be meeting.
Basically, if it's like physics, we're going to meet in here. If it's like chemical stuff, we're going to meet in Herm's room.
And if we're doing biology stuff, we'll also be in Herm's room. But yeah, so we'll be switching up the rooms depending on the needs of the particular meeting. So just stay informed. Same thing with Remind. We'll also be sending out reminders on Remind. So join that and be informed. Okay, so today, probably you guys have seen we're going to be talking about particle physics, which I've been told is a very boring topic, so I'm going to try and keep it light. Essentially, at the most fundamental level of physics is where we deal with particle physics. It's the tiniest of the tiny. It is when you go down to the atomic level, and then you keep going, and then you keep going, you're finally at the level where there is literally nothing smaller. There's nothing at a deeper level than the particle physics that we're going to be dealing with. So before we actually get into what particle physics is and how we study it, let me explain like what's the point of it? Why do we do this? Why are we talking about this? And I noticed conveniently there's like a bunch of handouts. I think Mr. Wilger just had these about different applications of like nuclear things with like energy and medicine, different things. Here's my list. A, it's the most fundamental level of our knowledge at this point. Anything new in particle physics is a completely new thing in all of physics, in all of human understanding. I think that's really cool because like you don't often think about just like in the modern day things being just never heard of before, but that's exactly what's happening in particle physics. And then on top of that, what we learn from particle physics helps us understand things at greater levels. So I think about chemistry. When we talk about atomic structure, when we talk about bonding and all that, it can all be boiled down more or less to protons, neutrons, electrons, even farther into the interactions between them. And so it's really just particle physics, but at a larger scale, right? And the same thing can be said of any interaction between any system, but obviously maybe it'll be a little bit more of a stretch. Some pretty common applications. I mentioned medical things between MRI, PT scans, treatment for cancer with radiation and things like that. There's obviously a lot of different ways that people can use what we learn in particle physics and what we learn in the lab to apply it to healing people and treating people. Chemistry, anything with nuclear chemistry, atomic structure, bonding, like I mentioned. All those things rely heavily on the way particles interact. I mean, chemistry is literally just the interacting of different particles, so obviously that's going to relate to particle physics. Telecommunications, when you talk about radio and the way things are being transmitted that way, that also can have tie-ins to particle physics. And lasers, radiation, and weapons. Recently I saw an article about something where they were able to keep a drone powered just by shining a laser on it. And the way that you can do that, the way you can understand what a laser is and why it works, is through particle physics. And that was something that I thought was cool. It kept, I mean, they're going to use the military and stuff, but yeah, so that's why we would use particle physics and why that's just important. So first thing we're talking about is the standard model. This is the handout you've each got. It's
If anyone has any like questions, you can just like, feel free to ask.
Oh yeah, totally.
Even like Mr. Logos.
Yeah, just raise your hand. Any questions, just raise your hand. Oh, yeah. So first thing, standard model. I like to think of it as like the periodic table for physics. In the periodic table, we deal with like all different elements. They've all got different numbers of protons, different properties. Some of them end up with different charges in their normal state. In the standard model, these are like at the deeper level. You've got things like an electron. Hopefully you've heard of an electron. And they've just got certain properties. And we see trends in the properties as we go in different directions, right? So same thing as a periodic table. So let's go through some of the important ones. probably you've heard of quarks. These are what make up things like protons and neutrons. And the most common ones are the up and down quarks. A proton is an up and a down. A neutron is an up and two downs. Okay, and the way they get bonded together is kind of complicated and weird. I'm not gonna deal with it. But yeah, when those combine, they form things like protons and neutrons. You also get other versions that are similar to them. Up is like a charm at a top, but these ones are heavier. So as you go farther to the right on this standard model, you get things that are heavier and heavier. And kind of a general rule, a general trend, the heavier something is, the less stable it is as far as particle physics goes. So like this top quark, it's got a half-life like so short they can never detect it. Literally, it took years and years in a lab before they could even detect the things that it was breaking down into. Okay, so just incredibly unstable because it's got so much mass. Again, electron, you probably heard of that. The heavy versions of an electron are a muon and a tau. We're going to be looking a little bit at muons later in this and things like that. And then neutrinos, probably you've also heard of those. Neutrinos don't really do anything. They're kind of like noble gases where they don't interact with other things and they're really hard to tell when they're there. But they're there, I promise. And they fill a pretty essential role in our little standard model. Okay, and so there are a bunch of different rules that kind of dictate how these different particles interact. So like I mentioned that there are ways that up and down quarks and other quarks will bond together to form other particles. So those are there are certain rules that will tell us how those can bond. You've probably heard of things like Coulomb's law, where different things with unlike charges will attract, and if they have the same charge, they'll repel. That still works at this level. You've got electromagnetic interactions, things like that. And I mentioned that the heavy particles will try and decay, they'll break down. Those decays are governed by a bunch of different conservation laws. So things like conservation of mass, you've heard of that, conservation of energy, conservation of charge. I noticed in AP chemistry they're doing a lot with conservation of charge this week. And essentially, you can't take something neutral and suddenly have something with a negative charge, right? Physics doesn't work that way. So all those different conservation rules will be important as we deal with this. The one last row on this table that probably you maybe haven't seen is, I'm going to move over here real quick, is what's called bosons. Bosons are essentially the way force is carried. It's kind of an abstract way of saying it, but that's what they call it. So you've probably heard of a photon, right? A photon will carry a force. It can be used to take an electron out of a metal. It can be used to conduct any sort of electricity. It's what actually mediates electric and magnetic fields. And of course, it's light, right? We've all hopefully seen light at one point in our life, right? By definition. Some of these other ones also do other things. The Z and W, what they do has to do with weak. With the weak force, but it has to do with beta decay, right? Beta decay from pre-AP chemistry, where you had maybe a neutron decays into a proton and an electron. Well, somewhere in there, Z and W will be doing something, okay? And so today we're going to be looking at Z and W and how they work. So this is the big fancy particle accelerator over in Europe. Who here has heard of the LHC? Anyone? See a few hands. Okay, so it's in Switzerland and France, and it's the world's largest particle accelerator, which is cool. And pretty soon it's going to start being under construction to be even larger, which is cooler. And the way it works is it takes these electric fields and these magnetic fields, and the magnetic fields will keep charged particles in place, and the electric fields will make them go faster. Okay, and so then over time being like a couple milliseconds or nanoseconds, over time they get faster and faster until finally something shifts and they're allowed to collide with each other. So most important, or generally it'll be things like protons. I think that's what our data was collected with. They'll take protons, they'll speed them up really fast, and then they'll slam them into each other, and all sorts of crazy stuff will happen. And that's where they'll be able to see what's going on beyond just the proton. Maybe they can see some quarks, maybe they can see some different neutrinos, They won't be able to actually see the neutrinos, but they can tell what's going on based on these high energy collisions. This detector here is called the CMS. It stands for the compact muon solenoid. A solenoid is a big coil that can make a magnetic field. It's compact because it's relatively small, even though this is like 50 feet across. Compact is relative. And muons are a type of particle. Let me see if I can pull back up. This is a muon. It's like a heavy electron. And what that compact muon solenoid does is it allows a very distinct track to form just from the muon. Okay, so then that allows us to distinguish muons from other particles, and that will be important for what we do today. Okay, this is just how we detect what's going on and how we can tell things about it. Okay, so W and Z bosons. I mentioned bosons are force carriers. That means like maybe you've got a proton and another proton that are like moving along. Well, they themselves in the particle physics world aren't just going to like hit each other and move away. Although we tend to think of it that way in classical physics. There will be some sort of force carrier. In this case, or in that case, it would probably be a photon. A photon would go between them, and it would be what makes them repel each other. W and Z also do that in terms of beta decay and things like that. But when you get those big collisions, you can actually have them existing on their own rather than just being a force between two particles. You'll produce like a whole Z boson, and it'll just be like going along and doing something. Okay, so now we're going to go into some of the rules of how they can decay. Because we'll never actually detect one of these bosons. They're so short-lived. But they can decay into other particles that we'll see, and then we can kind of think backwards to figure out what must have been produced and what must have decayed in order to produce what we're looking at. So first big one, charge must be conserved. Okay, notice a Z has no charge, a W has a positive charge, or W plus has a positive charge, and W minus has a negative charge, right? So if we can tell what charge is on this particle, we know what particle it is. Okay, and the way we'll tell what charge is on the particle is by what it produces. If it produces something with a positive charge, then it's got to initially have a positive charge. If it produces something with a negative charge, it had to initially have a negative charge. Often they will decay into muons. That's why it was important that they build that solenoid. But not always. Sometimes they can decay into electrons that are just moving really fast. The important thing is that energy is conserved. Usually that's done by having a heavy particle, but it can also be done by having a fast light particle. And what determines whether it's an electron or a muon isn't entirely known, and there may not even be a very deep mechanism. It might just be random. Sometimes quantum physics is like that. Another important one is that lepton number, the number of leptons in a reaction, is always conserved. Okay, this one is one that's a little more abstract than a lot of conservation laws, but nevertheless, it's out there. It exists. And the way we find the lepton number is we just count up all the leptons. Okay, pretty simple. And one thing I didn't mention in the when we looked at the standard model is every particle on there also has an antimatter particle. Okay, so like an electron and a positron, they're antimatter of each other, and so they look very similar, but they have opposite charges, and they can do weird stuff. We'll also have anti-leptons. A lepton, by the way, because I didn't mention that, is it either an electron or a neutrino? One of the electron things or neutrino things. I think it's labeled on your standard model handout. But anyway, yeah. So you can add up all the leptons and subtract all the anti-leptons, and that'll be your lepton number. It's got to be conserved in a reaction. Make sense? Straightforward? Okay. All right, so here are two examples of very common decays. Most of what we're looking at is going to be one of these. So let's look at this. So in this case, we start with the Z boson, and then it decays. Suddenly there's two particles. One is positive, one is negative, right? So the net charge is 0. Okay, everyone see why the net charge is 0? Yes. Well, that's good because we started with 0 charge. We ended with net 0 charge. So that conservation law is still good, right? Okay, another important thing, we've got a muon, which is negative, and an anti-muon, which is positive. Okay, and since we've got a muon, which is lepton, and an anti-muon, which is anti-lepton, the lepton number is still 0. Well, that's good because Z is not a lepton, so there you go from 0 to 0, that's lepton number is conserved. Okay, straightforward. With the W, it'll often decay into both a muon and a neutrino. Anything with a V is a neutrino. You don't really need to worry about that subscript. But note that the muon will either be positive or negative. Will either be an anti-muon or just a muon, depending on the charge of the W. Okay, that'll make sure that charge is conserved. And then the neutrino will either be an anti-neutrino or just a normal neutrino, so that the lepton number will cancel out and you won't have that all broken. Right. Now, one thing I'll mention: this is not what a particle looks like. Okay, this is a representation of the particle. We're not just going to be looking at a bunch of these in the lab, because those would be very nice. What we're going to be looking at looks a little more like this. Okay. In this, you have some big fancy particle that breaks up into 4 different particles. And who here's heard about a Higgs boson? Hey, okay, this is what a Higgs boson decays into, or one of the things it can. So the green lines are going to be electrons. The red lines are muons. And all the messy things in the middle aren't really part of it. They can be like just energy release. They can be anomalies that aren't accounted for, different weird things that aren't actually one of our decay products. But this is what it'll look like. Okay.